I'll take full credit for the questionable intro song.
Love
Do
it.
love some Talking Heads.
So strong.
Yeah. All right, hopefully we've given everybody a little bit of time to join, but I'd like to get us kicked off because we've got a lot to talk about today. So for anybody who doesn't know me, I'm Carly Anderson. I'm a chemical engineer and a partner here at Prime Movers Lab. I'd like to start by welcoming everyone, our limited partners, founders, extended PML family, and those just curious about this topic. For anyone who's new, Prime Movers Lab is a deep tech venture capital firm investing in breakthrough science companies that have the ability to transform billions of lives. This means we're investing in the building blocks of civilization, so companies improving human health span, agriculture, manufacturing, transportation, energy, and the infrastructure that supports all of this. The companies we work with are also solving some of the greatest challenges facing humanity, including climate change. So some quick housekeeping, we will keep this to an hour. And I highly encourage you all to use the chat or the Q&A feature to ask questions at any time. We will weave some in as we go, and we will leave some time at the end for questions. And with that, perhaps the more exciting thing is today's topic. So emerging carbon sequestration markets. As we've all seen from the figure from the IPCC, we need to remove 10 gigatons or 10 billion tons of CO2 from the atmosphere by 2050 or else. Right? Loss of land, loss of species, bad weather, fires, dead coral, like lots of bad stuff. So if we need to remove 10 billion tons of CO2, where will it go? And on top of that, we're still emitting 35 billion tons of CO2. What do we do with that? You know, the world produces about 4 billion tons of cement each year, maybe double that for fuels. By my math, that means the rest of it needs to go somewhere. And as the people on this panel are all involved with, underground seems like a great place to put it. So with that, I'd like to ask our panelists to introduce themselves. We've got one of our founders, Adrian Corliss from Carbon Capture, and two outstanding experts from the CO2 sequestration industry that is forming Rocky Robbie and Dick Longquist. So maybe Adrian, you can kick us off.
Sure. Yeah, thanks. And appreciate the invite and glad to be part of the panel today. So I'm Adrian Corliss. I'm CEO of Carbon Capture Inc. We're a Prime Movers Lab portfolio company based in Los Angeles. So we're relatively young. We're about 35 employees, growing fast, but we're a company that does a couple of things. First is we have developed and manufacture machines that will capture and remove CO2 from the atmosphere. And then the second part of what we do is actually to develop projects where we're linking the direct air capture machines with either sequestration partners, so it could be companies like Frontier or Longquist that will take custody of that CO2 and permanently store it. Or we're also looking at projects that are utilization of the CO2 as replacement or substitution for fossil carbon and synthetic fuels, or also as a way to augment through mineralization of cement the quality of the cement. So basically another place to permanently put CO2. So those are the things that we're working on. Really excited that we're just in the early stages now of developing projects in all three of those areas. So I think that our goal is to have first machines on the ground in 2023, and basically the way we're approaching this is we have a modular piece of technology that we can start small, but on a particular project, we can grow that project up to megaton or greater scale. So it's all about using the benefits of modularity to reduce risk, to decrease development cycle time, and to get ourselves in front of more customers.
All right, thanks, Adrian. Maybe Robbie, where are you joining us from, and tell us what you're doing.
Hey everyone, thanks for the time today and joining us. I'm Robbie Rocky, CEO of Frontier Carbon Solutions. We're a portfolio company of Tailwater Capital. I'm joining everyone from a hotel lobby in Cheyenne, which has kind of become my second home. We are a carbon storage developer, so we work with emitters or emissions partners to acquire and aggregate the leasehold, the pore space leasehold for carbon storage. We do the downhole work and reservoir characterization. We file the Class 6 permits for carbon storage, and then we also do the right-of-way pipeline and compression modeling to kind of accelerate decarbonization for a variety of kind of industrial partners. Focused predominantly in the Rockies. We have a project in Wyoming and then one in Alberta also.
Awesome. All right, and Dick, can you close us out?
Sure. Hi, I'm Dick Longquist. I am chairman of Longquist Sequestration. It is a spin down of our bigger parent company, Longquist and Company. We're an injection engineering firm. So we help our clients inject stuff into the earth. And lately it's been CO2, but we've been around for decades helping inject all kinds of stuff for EPA class 1 through class 6. We're about 90 people in 8 offices. We have 6 offices in the US and 2 offices in Canada. And we'd had CO2 sequestration as a line item on our website for the last 19 years. And until the government instigated the tax credits for this, we never got one phone call. But we're currently working on about 70 projects in about 18 jurisdictions in the US and Canada.
Thanks, Dick. So, wow, it really sounds like things are moving. 70 projects. How does CO2 sequestration play into, do you all feel like the bigger picture, right? Clearly things are moving. Like, how far did this go? How do you see this space evolving? Let's start high level. Maybe Adrian, do you want to take that one? You're muted.
I'll try that. Looking at the, obviously, the idea of net zero by 2050s, it's a concept that's, I think, accepted and well known, and it's the target we're all shooting for. But I think it's really, getting to net zero is a math problem. And so, when we're looking at 40 gigatons of emissions today, where are those 40 gigatons going to go? A big chunk of them needs to go through just emissions reduction. We need to emit less. And so, whether it's electrification or efficiency, those sorts of pieces of reduction emissions are important, but that's not going to be enough. So, the next big thing is really going to be point source capture of CO2 and permanent sequestration. So that's obviously the first place where sequestration needs to be done at scale to deal with the point source emissions that either can't be replaced or can't be replaced fast enough. And then you're still, of course, math is not getting you to zero yet. So there needs to be a carbon removal piece. And right now, I think it's predicted to be at least 10 gigatons a year for carbon removal. And a big chunk of that is likely going to be engineered solutions like direct air capture, coupled with permanent geological sequestration. So it's kind of the second place where sequestration plays in. So I think without, again, the ability to put CO2 back into geological formations, the math doesn't work. So I think that's kind of a big picture. It's just a necessary part. And it's going to be like tens of gigatons per year going out at least till the end of the century.
Maybe Robbie or Dick, do you want to chime in on how you see this space going? Or why now?
Yeah, I mean, our sense is that carbon storage or sequestration is just the bedrock of successful decarb. There are just some industries that are impossible to abate. And so they have to have CCS. And then, we look at, just like Adrian said, there's an avoidance component that has to be addressed, and that needs to be paired with an increasingly robust removal component from direct air capture. But, I think what gets a little bit lost in the narrative is that we've been successfully storing CO2 underground in the US for more than 30 years safely. So it is very well understood. Just that a lot of that knowledge is sort of buried inside the oil and gas industry, and the ability to kind of take that out and apply it to a lot of these other things and marry up all these verticals. Feels like we're in the early days of what will be a very successful enterprise to deploy CCS at major scale.
I see what you did there with the knowledge is buried. I liked it. So okay, so what I've just heard, and I think Dick alluded to earlier, is that we already know how to put CO2 underground. We're putting CO2 underground today. How hard is that? Is that just something you can do anywhere? Is that something that you need specific geologies for? Can you say a little bit more about how, like, what is really well known and what is a little bit less known and still needs to be done in this space?
Sure, I'll take that one. We've been injecting CO2 into oil fields for for decades and decades to get more oil and gas out of the ground. So from a technology standpoint of moving CO2 around and injecting it into the earth, very well known. The sequestration part's kind of what's new, and what's the newer components on that side is the permitting, which is new or relatively new, and then the capture side. So, you know, once you hand somebody as an injection engineer like me your CO2, pretty well known how to get it into the ground. Regional wise, we're seeing a lot of probably about 80% of what we're working on is along the Gulf Coast. And there's a couple of things going on with that. One is there's a lot of smokestacks with the oil and gas industry, and there's a lot of good rock to inject into. You know, there's other great places to go. You know, Robbie, no accident, Robbie's up in Wyoming. It's a very, very good permit environment, or at least I'm sure he's hoping it is, compared to dealing with the EPA.
Yeah, I think I'd follow on that. You know, we like the Rockies for a couple of reasons, but you know, when we think about how long we've been doing this, you know, in Wyoming for nearly the last 30 years, we've put about 6 million tons in the ground per year for CO2 oil recovery. So it's, I mean, that's, you know, a couple 100 million tons safely stored, you know, in, you know, the huge body of evidence of how to do it, and how to make sure we know where it goes and where it stays. And, you know, as Dick alluded to, you know, we like the Rockies, just it's a little easier regulatory framework to accelerate projects. And it's a place we just have a little bit more internal alpha. But, you know, what Dick's focused on there, a huge emissions profile on the Gulf Coast, and that will long term be in an enormous place for a lot of these hubs and a lot of this CCS expansion.
Okay. Well, and Robbie, thanks for putting some numbers on, you know, 6 million tons per year sequestered in, or put underground in Wyoming. I think I've read somewhere around like 300 million tons used in the US for enhanced oil recovery each year. So it sounds like we're still talking about at least an order of magnitude increase to gigatons, to get gigatons underground. Would all of that fit in depleted oil and gas wells? What about saline aquifers? What about some of the other geologies we might read about? Are those important as well? And how do you see that breaking out?
Yeah, right now we're seeing about 90% of what we're looking at is saline aquifer type projects. You absolutely could put it in depleted oil and gas fields. You know, the problem gets to be is the EPA and or the state who's acting on behalf of the EPA is going to make you deal with all those old oil wells. So if you want to take an old oil field and start putting CO2 in it, you might have to spend a lot of money to recondition the wells to do that. So we're seeing a lot of folks look at saline aquifers, whether that's US, Canada, and or around the world.
I think Dick brings up a really good point about trying to repurpose old oil wells. There's just a lot of kind of hidden risk in doing that. You know, our focus is on deep saline storage, you know, beneath all the hydrocarbons that are below all the oil and gas production. For a sense of scale, Carly, you know, the first zone that we've started work on, you know, the calculated kind of storage resource in place is about 18 to 20 million tons per section. And so that's like, if you think of an oil in place number for an oil field, that's kind of our storage in place number. So not all of that can be displaced and fully stored with CO2, but it, you know, those are big storage capacities per section or per square mile. And you can pretty quickly, you know, visualize an area that can store that gigaton. It's not as big as I think, you know, folks would think to believe initially.
Okay. Thanks. And maybe Adrian, I can get you to chime in on some of the mineralization approaches, which is, you know, something else. I know we've probably a lot of folks on this call have heard about projects in Iceland with Climeworks and some others. What's the difference between mineralization and using a saline aquifer, for instance?
Yeah, we have a partnership and also a strategic investor in Rio Tinto, and Rio's got certainly global ambitions to use their geological assets where they have the right geology, and for mineralization, typically you're needing a younger volcanic type rock. So you're going to need mafic or ultramafic rocks that have basically the ability to bond to CO2 to form carbonates, and effectively what you're doing in those geological formations is forming either calcium or magnesium carbonate, which is basically another form of rock that's going to permanently sequester the CO2. So there's a lot of people that like that idea because of the permanency and the fact that the mineralization can happen over months as opposed to the permanent storage of gas. So there's a permanency, and I would say a reduction in the need of monitoring, which is appealing to people. And I think there's I think that appeal of not being concerned a year or two down the road about where that CO2 is going to end up down the road. So I think that's sort of the appeal of it. Turns out also that the US has got really good formations for mineralization, and Rio is developing a nickel mine in Minnesota where they happen to have a lot of ultramafic rock that's well suited for mineralization as well. So kind of in the many gigatons of capacity at that one project as well. So since that's a project that's focused on electrification and nickel for EV batteries, it's great that it also can have a component of carbon removal as well. So I think there's it's another sort of area where gigatons of CO2 can go, and you kind of look globally, it's hundreds of, if not thousands of gigatons of capacity into mineralization that are relatively shallow reserves. So in Iceland, the wells that they're drilling to do the mineralization there are somewhere in the range of under 1,000 feet. So obviously it's it's as opposed to maybe as much as 10 to 12,000 feet for some of the saline aquifers. So there is some reasons why people are quite interested in that as well.
Thanks, Adrian. And maybe I see a question that's fairly relevant that just came in to some of those different levels, like where underground the CO2 is going, how you make sure the CO2 that's being injected into, say, saline aquifers doesn't disturb potable water that could be underground. And I know that's a whole nother question about where is there potable, where is the groundwater brackish and all of that, but maybe from a sequestration standpoint, how do you guys consider that in assessing a site?
I'll jump in. So I'll give an example, and this is a gross underestimating of the science. But with saline aquifer sequestration, the best example I have is if you had a can of Coca-Cola and you put it on your pantry shelf for 25 years, and you came back out and you popped the top on your can of Coke, it's going to be flat. And so there's a lot of stuff going on geochemistry wise, pore space wise, mineralogy wise with aquifer sequestration. But the quick answer is the CO2 long term will stabilize in the reservoir, and it'll react with the rock, it'll react with the water, and it becomes safe over time. So the EPA is involved and has pushed that authority down to certain states. Wyoming is one of them. North Dakota is one of them. We're probably weeks away from having Louisiana have authority to regulate on behalf of the EPA, but that's their sole goal. All this comes down through the Safe Drinking Water Act of 1974. It was put in place to protect fresh water. So the EPA and their surrogates, like in Wyoming, that's what they're there for. They're there to protect safe drinking water.
So in other words, like ensure that there's a non-permeable layer between the potable groundwater and the pore space where the CO2 is. So basically making sure that there's geology that doesn't let the CO2 go into the groundwater. Is that
exactly
correct? Okay. And maybe speaking to that, like Robbie, I know we've talked about this. How do you make sure that the CO2 is down there? Like how do you image it or track it, et cetera?
Yeah, so I mean, to what Dick was talking about, that's the most. I mean, taking a step back, that's the most robust component of the permit application. I mean, you need a 1,000-page application by the time these things are filed, and you spend 6 or 9 months doing reservoir modeling, simulation modeling, just verifying when I inject CO2 into this particular rock, how do I know where it goes, and what is that plume, as we call it, how's that shape over the next 10, 20, 30, 40, 50 years? One of the best tools we have today for imaging CO2 plume movement is seismic. Our background, we operated a very large CO2 flood in Wyoming. And as we added CO2 into each phase, we shot seismic every couple of years, and we were able to see exactly how that plume moved throughout that reservoir and make adjustments to other wells or other injection rates to kind of control the flow of it. And so it's really well understood how it moves, but there is a very high bar for one of these injection permits, and you really should need to do your homework on how these reservoirs accept CO2 and what we know and how they'll behave. Sandstones are just kind of the most well understood, but you're seeing some work done on some of these other alternative reservoirs too, which I think will be interesting over time.
Well, just as you're talking about this, and this is an unfair question because I didn't tell you I was going to ask this one, but can you give folks a sense of how much does this pre-work cost in terms of like order of magnitude, right? Like how much development work does it take to get a project started? Are we talking like 100K? Or are we talking like $10 million? Like,
yeah, it's a fair question. I think it's a barrier to entry. We're going to file 3 permits here sometime in the next kind of 60 days, and we'll be well over $1 million, north of a couple $1 million in kind of full on, seismic purchases, seismic acquisition, reservoir modeling, out of all the monitoring, reporting, and verification. So it's a very, very high financial burden just to file a permit, let alone meet some of the financial assurances that these various jurisdictions are going to require.
Yeah, and just to give you an idea, and Robbie's right, that the amount of effort in these permits is 10, 20 times more than any of our other permits we deal with. The EPA is estimating that their review time, so the time it's going to take the EPA, if you're in an EPA state, is 1 man year to review the permit application. So if you're not in Wyoming or not in North Dakota, and you're in an EPA jurisdiction, it's enormous amount of time. We're telling our clients right now, they're coming in, an estimate of cost to prepare a Class 6 permit. We're saying $700,000 to $1 million to prepare and submit 1 permit. And so within Class 6, each wellbore is a permit. So if you, like Robbie's project, if you have 3 wells, that's 3 permits on the Class 6 side.
all right. We're really demystifying the exciting world of permits here. Bless those people at the EPA's heart. And maybe, Adrian, you can comment on the other side. I'd love to hear, what are you hearing from the markets? What are they asking for in terms of verifying that the CO2 stays down there? So clearly these companies are spending a lot of effort with the EPA. Yeah, what do you hear from the other side?
Sorry about that, Carly. I think, from looking at this in the context of carbon removal credits and actually the generation of revenue from carbon removal, in the US anyway, it's likely going to be a combination of tax credits generated through the 45Q program. And then beyond that, on the carbon removal, there's really voluntary credits being purchased by, at least in the early days, large profitable companies that can afford to pay a premium and get the market stimulated. So, at least at the beginning, there's not really there's not bodies that are certifying the carbon removal. So there's certainly the companies that are out and making early purchases of carbon removal. Generally, they're hiring their own team of experts to try to make sense of what's going on and do an evaluation of whether they think that the project is actually net removing carbon. And they're relying on things like the Class 6 well certifications to give them basically the assurances that the projects were done correctly. But I think right now, it's like I say, it's early days. There's not really established sets of processes that are out there. So it's hard for example, a small organization who doesn't have the PhDs on staff to kind of figure this out. And that's why I think there's, what we'll see is a few aggregators that are out there just helping smaller organizations if they want to participate in carbon removal. But it's still really early days. And these guys will know, even in the context of the whole US, if I've got my numbers right, there's only 2 Class 6 wells that have been approved. And so there's $3.5 billion set aside for direct air capture hubs, to basically get this at the megaton scale quickly. Yet there's not any place to put the CO2 yet because of the burden that the same government is putting on the actual certifications of wells. Alongside the fact, as you said, they're okay with the hundreds of millions of tons that are being put into the ground in the context of oil production. So there's a kind of a mess there that I think is going to take some time to clean up.
And just to make sure it's clear, when we talk about Class 6 wells, we're talking about, that's the name or designation the EPA has given to wells that sequester CO2, right? As opposed to wells where you would inject CO2 for enhanced oil recovery, and that's a Class 2 well, I think. Is that, okay, so Class 6.
That's correct. Class 6 was created about in 2010, and it's exclusively reserved for CO2 sequestration. Class 2 was created a long time ago, and it's reserved exclusively for oil and gas operations. And so Class 2 plus MRV, which is another way to get to the 45Q tax.
And MRV is?
MRV is monitor, report, and verify. So there's 3 mechanisms. There's EOR, there's Class 2 plus MRV, and there's Class 6. And those 3 ways are ways to get to the 45Q tax credit. So there's only a few states you can do Class 2 plus MRV, because for the most part, it involves states that already allow hydrogen sulfide, H2S gas disposal. And there's only a handful of states that allow that.
So Dick, can you actually put a Class 2 well into a saline aquifer, or is it really by definition into an oil and gas reservoir?
No, you can put Class 2. You can put it into saline aquifers for sure. We've been injecting H2S, which is a oil and gas poisonous gas byproduct. We've been doing it for decades, and it'll go into saline aquifer.
Okay. That sounds super exciting. I definitely want to tour that facility. Yeah.
Yeah.
So speaking of these facilities, so what are the most expensive parts of sequestration? And now I'm wondering if I already know the answer, and it's permitting. But I figured, when you're looking at these different geographies, looking at these different types of rock formations, or looking at, is what makes you guys excited about one area versus another, or a new technology versus another one?
Yeah, I'll go first. And we've heard permitting is expensive. With that is the cost of the well. Part of that permitting is you're basically designing a well that once you build it and construct it and start putting CO2 in the ground, you'll have materials in there, so you never have to put a rig on it again. And we're talking about pretty high volumes of CO2. So a Class 6 injector uses, chrome alloys, nickel plating, all these things that are pretty high dollar jewelry, if you will, for wellbore design. So your Class 6 wells can be $7, $10, $12, $15 million, sometimes even more. Pipeline transportation. So just a pipeline, directionally is about $1 million a mile to build a pipeline pressure rated to ship CO2. And then the kind of the last piece on the shipping and injection part is compression. CO2, most of the times it's captured at atmospheric, or the kind of ambient pressure. We need it at, about 1,400 or 1,500 pounds per square inch of pressure. And so it just takes a lot of iron and a lot of horsepower to get it compressed up to that stage. We do that because once it's compressed to that stage, it behaves a lot like a liquid, and we can pump it around, which is a lot more efficient and just a lot better for long-term injection. So compression, pipelines, and the wells are the 3 biggest kind of capital drivers, which, you kind of to your last point. So you want to look for areas where you've got a big set of emitters, close to really good storage. So you've got kind of those right on top of each other, and avoid really, really long pipeline runs or issues where your CO2 purity is hard to kind of get it to that higher purity.
Okay. How many tons of CO2 can go down one well?
So, I mean, depending on the design, probably up to 1 million. We're permitting ours for 500,000, and we've done modeling for 500,000 per well, up to 1 million. But then it becomes some nuance in kind of how your flume behaves and the size of well you drill, and some of the economics of scale there.
Awesome.
We're doing some on the Gulf Coast in bigger, thicker packages of Miocene sands that are probably 2.5 million tons a year per well. I think it's rock specific. So depends on where you are and what kind of rocks you have.
So basically you need good rocks, you need a lot of CO2 close by, and you probably need some sort of a power source. I know, Adrian, this is something that we've talked a lot about. Like, what else do you need around what do you need for a successful CO2 sequestration project?
Yeah, well, I think with direct air capture, it's a little bit different in the fact that we're looking for, and we're able to actually go and find the right locations where you have the right geology and also the right sources of inexpensive and low carbon energy to actually power direct air capture systems. So, it's a little bit different that way, where we're actually able to be pretty selective and and flexible in where we put our systems. But you're right. I mean, compared even to the compression side of CO2 injection, the energy required to actually separate atmospheric CO2 into it and get it into a pure form ready for sequestration is probably an order of magnitude more energy than that again too. So it's an energy intensive process. So you have to be thinking about not having energy sources that are going to be additive and basically undoing the net benefit of the removal. So again, that's always a big part of what we're looking for is what does that low carbon energy look like, and where is it coming from, and how does it not undo the economics of what we're trying to accomplish.
Cool. And hopefully that kind of gets to one of the questions in the chats too. So I think where that was leading me is we talked about the expensive parts of sequestration. What CO2 pricing is required from governments, et cetera, to make these projects economical? And I know from just like a financing standpoint, like this actually doesn't sound, that bad. Like things in the $1 to $10 million. That's a lot better than trying to build like a, $100 million or like $1 billion plant, or potentially a carbon capture system bolted onto a power plant. It's going to be a lot more than that sequestration piece. So even though a couple $1 million, maybe that's small in the grand scheme of things. But what CO2 pricing do you guys see as necessary to get this really accelerated?
Well, I'll start off, for the listeners that don't know, 45Q is currently, let's call it in the $50 per ton range. It has an escalator in it. But I can assure you the winds of change have come, and all the companies we're working for, in fact, one of them came in and said, even if there wasn't a tax credit, our shareholders have told us to go start doing something. And they said, we're going to do this with or without the tax credit. And they basically said, look, my shareholders want a shiny picture on page 4 of our annual report spelling out what we're doing. And, you'll hear a lot of people say that you really need about $85 a ton. That's the number that was in the Build Back Better bill that did not pass. So I think the market would like the $85 a ton, but is
that for us capturing CO2 emissions, or is that direct air capture? Is that across the board?
That's across the board. But yeah, we're seeing projects that we think are going to lose money even with the tax credits, that are going to go to final investment decision and are going to get built.
Interesting.
Yeah, I'd echo some of that. We're seeing a post-combustion carbon capture, so off of a power plant or a boiler or some of those things, depending on some of the nuance, it's $50 to $70, for capture and storage, and that's really how far you need to run for storage, some of those things. But 85, is certainly a threshold to accelerate a lot of these products. On director capture, I think it's 150 or 130 that's proposed in kind of this next round, which would certainly help. But all these things are strengthened by the voluntary offset market that Adrian mentioned earlier, and that really helps bridge the gap when you think about building a commercial revenue stack for one of these projects.
Yeah, and I think it's actually the proposed language. It's $185 for DAC plus sequestration, $150 for DAC plus utilization. So that was, and I think the other two pieces that are really important in that that our challenges right now is the minimum project size is 100,000 tons per year under the current regulation. So it's tough to get a small project started if you're a smaller, earlier stage company doing direct air capture. And then the final piece is changing it from basically a tax credit to a direct pay. So, being able to go and unwind some of the complexities of having tax equity partners playing as well. And again, just sort of simplifying how smaller projects could be rolled out. So again, I think the good news is that that 45Q bill and the changes have bipartisan support. It's just, it was attached to too much other stuff that was complicating it. So I think, again, I don't know, Dick, Robbie, you guys are probably even closer to it than I am, but I think there's still people that are hopeful that one way or another, those changes will get in through, some other mechanisms in the next 12 months. And, it certainly will help.
But Adrian, are you saying that the US tax code is complicated?
I'm Canadian. I don't know.
Okay. Well, actually, maybe you could.
I think Adrian's right. Our understanding through our clients, lobbyists, is that the language is sitting there waiting for a bill to attach itself to that will bipartisan support.
Awesome. Well, and Dick, actually, another question came through for you. Given your focus on Gulf Coast projects, do you have any opinions on Denbury and how they are trying to build their CCUS business? So I think Denbury being one of the biggest CO2 pipeline controllers in the US, especially in the Gulf Coast.
Yeah. So Denbury, what I call the legacy players, so Denbury, Oxy, Hillcorp, Chevron, these are guys that have been in the CO2 enhanced oil recovery business for a long, long time. And I think Denbury's pretty well poised. We sure see them in the marketplace a lot. They have a pretty good pipeline backbone running the Gulf Coast. So they're kind of in a unique advantage of being able to partner with people. So when you're the only guy in town that has the infrastructure backbone already in place, all of a sudden you're kind of the prettiest one at the dance. So I think they're poised very well for the market.
And so how would that work? Do you think we'll start seeing people, put captured CO2 just into the regular pipeline, and just a molecule of CO2 is a molecule of CO2? You can take CO2 somewhere else out instead and do accounting like that?
Well, there's people that have CO2 smokestacks in one place, but the geology they want is not there, but they might be able to buy transportation from Denbury and have Denbury be a transportation partner. So they're just hauling the CO2. Denbury also, there might be other mechanisms where Denbury would buy or take the CO2 to continue their oil and gas operations.
And do you guys think that the government will recognize the molecules are the same on both ends of the pipeline? I know like California low carbon fuel standard, if folks are familiar with that, I think that does something similar where a molecule is a molecule and they're okay with that. But there's always the argument that is this just enabling bad behavior on the parts of some companies by giving folks an easy out?
Well, the 45Q already takes that into account at some level, because the tax credit for EOR is not $50, it's $35. So they've already made it a lesser tax credit, on face value of it. But there's going to be We're already seeing it on the permitting side. I'm sure Robbie will have some comments on this, but there is going to need to be some cleanup legislation at the federal level and at the state level in the various states that are going to end up having primacy. Because there's just a lot of stuff that nobody thought about now that we're actually starting to do this, that, we're like, the law didn't anticipate, this question or this problem or, this scenario. So we think there's going to be multiple rounds of cleanup legislation as this industry evolves.
Yeah, I think we're seeing some of it. Wyoming, for example, just passed SF 47, which is a bill that addresses post-injection liability. And that's the question, like, all right, so what happens after the storage site, is plugged and abandoned? Who ultimately, where's the liability? So in California, right, it's contemplated to be 100 years, which is kind of a deal killer for any projects. The state of Wyoming said, hey, after 20 years, if it's plugged for the DEQ requirements, the state will take custody of the liability. And so that's just one example of to what Dick alluded to, the things that are emerging in this very nascent industry. But there are pore space ownership, post-injection liability, all the permitting. These are things that are getting, I think being thought through, actively in all these jurisdictions today.
And Adrian, like, what are you seeing? I know, what are you seeing up in Canada, maybe,
Yeah,
or some of the other parts? Yeah.
Yeah, and I think Robbie knows this probably really well, as well, because he was mentioning earlier they have projects under development in Alberta. But certainly the Canadian government has taken a different approach, where 45Q is really about an OPEX. Basically subsidy for actually operating a sequestration facility. Canada's taking a different approach in doing an investment tax credit specific to basically buy down the capital of certain projects. And so what they announced recently is pretty exciting, is for direct air capture plus sequestration, not into an EOR, well, it can't be for EOR, that they'll have a refundable tax credit of 65% of the capex of the project. So that's a pretty big deal, and that's potentially stacked up against other provincial opportunities for either operating benefits or capital benefits. So I think that they're making a pretty bold statement that they're going to invest heavily in getting carbon, direct air capture and sequestration. But it's, I think, for point source capture and sequestration, the ITC is 50%. So it's still really significant.
And one other unique advantage of Canada is all the pore space in Canada belongs to the Crown. So when you want to go put together your acreage position, which is challenging in the United States, it's very simple. There's one person to go talk to in Canada.
Yeah, that's interesting, and that's one of the things that I've learned over the last few months is the difference between mineral rights and pore space rights and who owns them. And as I now understand, the pore space is actually attached to the surface landowner, whereas mineral rights can be separated. And I can understand too. It's just a whole and if your plume gets outside of your the space that you've leased, you're effectively trespassing on the neighbor's property.
I'm so glad that you guys have read through all this, so I don't have to.
Well, and really there's some unforeseen consequences. We're already seeing, the U.S., which is more litigation prone than our Canadian friends. What if you have an oil field at 8,000 foot deep and you want to put a CO2 storage project at 6,000 foot deep? Now the oil field guys have to drill through your CO2 plume to get to their oil field. Have you created a drilling hazard? Is it going to cost them more money? Are they going to sue you for the drilling hazard you've created? So, these questions are already coming up. We're dealing with them in our office already.
Yeah, legal thriller around CO2 sequestration. I can't wait. Great. So I guess another question is a little bit off on another topic. How much energy in kilowatt hours do you estimate is needed to capture and sequester, say, 1 ton of CO2? I think what would be kind of interesting there is, for capturing CO2, how much energy does it take? And then to take your ambient temperature CO2, ambient pressure CO2, and put it underground, how much energy does that take roughly per ton? How many windmills do we need in Wyoming?
That's a really good question, Carly. And admittedly, like we haven't done the work on a kilowatt hour analysis. It's mostly a raw capital number analysis. And that's
Okay.
threshold one. That's how much does this cost? But it is energy intensive. I mean, when we think of the OpEx, if you will, operating cost for a post combustion capture system, it's really two pieces. It's half of it is the cost to run the compression to get that gas to pressure, and the other half is to generate the steam needed as part of the CO2 recovery process from the carbon capture plant. And so it is, I mean, directionally, I mean, think of that as $20 to $25 per ton from an operating cost perspective, handle one of these big facilities.
Well, and when you're talking about steam to remove the carbon capture or the carbon from the capture facility, you're talking about like carbon capture devices on smokestacks, like point source plants, right?
Yeah. Just it's you have one tower that where a solvent or a liquid absorbs CO2, and then you run it through a second tower, and you just hit it with a whole bunch of steam and break out that CO2. And so the energy to create that steam is about half of your operating cost. And then you take that high purity CO2, compress it, and ship it. So those two pieces, compression and steam, are really the biggest drivers in operating cost for post combustion. It's certainly different for direct air capture.
And so for compression, that's on the order of $10, $15 per ton, or less.
Yeah, we think of it's about half and half when you think of it sort of it's.
Cool.
Yeah, and for direct air capture, it's a different energy equation, and I think that as it turns out, like, so from the thermodynamics of it, it's actually not as punitive as people would think. But I think still, practically speaking, you're probably looking, in early days with the materials we have available to us now, somewhere 7 or 8 gigajoules per ton. And I know it's not kilowatt hours, but there's certainly pathways to get that down under 5 gigajoules per ton in terms of direct air capture energy needs.
Cool. Right. Thanks, Adrian. Now, I think we've got a little over 10 minutes left. So just a quick reminder to folks, if you have questions, get them in now. And maybe we can shift a little bit towards looking even further into the future. And I'm curious how, you guys are thinking about potentially putting CO2 underground so you could get it back out, right? Like, I think we talked a lot about sequestration, permanence, and we didn't really touch on the advantages there versus some of the other approaches that trees can degrade and stuff like that. Do you see there being a future where Robbie and Dick, you're putting CO2 into caverns and taking it back out, making fuels out of it, etc.? Or Adrian too.
Out of the 70 odd projects we're working on, we're only working on one that involves salt caverns. It's been verbally disallowed in Louisiana. So Steve Lee, the regulator, is not going to allow salt cavern CO2 storage in Louisiana.
Why not?
Louisiana has a different regulatory history than let's say like Texas or Wyoming. And, for the better part of 30 years, they've been on double secret probation with the EPA for some past issues. And so they're hyper focused as compared to maybe other jurisdictions. But Texas, the one project we know of we're working on is in Texas, and that would involve pulling it back out for other uses. If you put it into a saline aquifer, unless you pull it out real quick, let's say the first 10 or 20 years, you probably won't be able to get it back. And either way, you're not going to get it all back.
Okay. And maybe that's good.
Follow on that. Yeah. I would say just to follow on that, we design everything with the idea that it's permanently stored. But one of the topics that always comes up is, what happens after year 12, right? The way the tax credits, they expire after year 12. So how do you create that commercial case beyond that for storage? And what we think we're putting predominantly pure CO2 into the ground. And kind of alongside all this emerging industry, we're seeing, the utilization industry really get accelerated with capital. And so things like synthetic biology, the ability to create, something like a nylon with CO2, aggregates and these other things. And so when we think about what does the next 10, 15 years look like, our expectation is that we may have big storage resources, but perhaps not all of that CO2 is going into the ground. Some of it is being diverted off for utilization and permanent storage in other manners or other materials on the surface.
So we're really talking about sequestration, not storage, even looking out yet 10, 20 years from now. Adrian, what other comments do you have on utilization?
Well, I mean, I think at the end of the day, like there's this idea of in terms of what's being put into the atmosphere now from the combustion of fossil fuels, and only about 10% of it is used for other than fuels combustion. So at the end of the day, the market for CO2 isn't big enough, like on the utilization side, to solve the whole problem anyway. So I think there's always going to be enough CO2 that could be sourced for utilization at the surface without kind of undoing some of the sequestration you've already done. And I also think that the credits that you've generated and the people who, and the things that you've done, in those first 12 years probably aren't going to allow you to take it back out, and given that was intended to be permanent. So my view is that, like if it just does, to me, it's such a big problem that I think you got to view everything we're doing now as permanent. And if you need CO2 in the future, there's lots of it, in the atmosphere to work with.
Couple gigatons we need to take out, right? Something like that available.
More than a few, yeah.
Yeah, just yeah. So I guess kind of wrapping up, and what do each of you see as the biggest challenge that needs to be overcome to make this go even faster? And the question I'm going to ask after, so I'm going to give you some time to think, is how many gigatons will we have put underground in the next 10 years? Your crystal ball prediction.
Yeah, my just because we do a lot of this is the permit process and the permit timeline. Robbie's up in Wyoming for a very good reason. Wyoming has primacy, and he's going to get his permits quicker in Wyoming, and he can be in business quicker. If you're in Louisiana or Texas or along the Gulf Coast or any of these other states that are still nominally regulated by EPA, it's going to be 3 to 5 years to get your permit. So it's a long way to the point where you're going to get in business. And these are expensive projects. So we see the permitting timeline of 1 man year to process a permit is the 800-pound gorilla that's in the room. It's really want to get moving, you're going to have to do something with that timeline. So
I will attach a link to find your senator's address to the YouTube recording. Is that what you're saying we should do here? It's a matter of hiring people. These are Robbie will tell you, these are very technical permits. This isn't, handed off to a regulator. These regulators are engineers and geologists and geophysicists, and as a country, we're going to need to hire thousands of those at the regulatory level to keep up with what's the onslaught that's heading the way of the regulator. All right. Tell your kids to be
Carly, I wish I had a different one, Carly, but mine is the same as Dick's. The acceleration of the 45Q permit process. That's for point source capture technology to continue to mature and cost to come down, for DAC, for all these things to continue to mature and this cost to come down, you need storage, and to accelerate storage, you need a faster permitting process. And I said in the beginning, but it's, this skill set is very, very well understood in our industry, and it's exciting to be a part of the pivot, if you will, to take that and apply to this, and hopefully, be part of that engine to accelerate this place.
Yeah, and I think for direct air capture specifically, it's again, right now it's been great the last 4 or 5 months with the I would say the commercial commitments to buy direct air capture or carbon removal credits at their actual cost. And then the whole goal is to buy enough of them to drive the cost down to where you can have a much broader set of customers paying to offset their emissions or the scope 3 emissions that they can't get to within their organizations. But I guess the question is going to be, is there going to be enough? Is that demand going to be enough to actually drive the cost curve down? And will people and the broader industries actually continue to have the willingness to pay a premium to offset the emissions that they can't either reduce or capture at source? And so I think there's we all know where we need to be in 2050. We have a really good starting point right now with what's been going on in terms of commitments for carbon removal. But there's the pathway between the first couple million tons and 10 billion tons is pretty unclear.
Well, I'm glad that there are smart people like you guys working on this, right? That is the awesome. All right, so going into how many, okay, last question. What do you hope to see 10 years from now? But how many tons do you think of CO2 will be injected underground? We'll say the US, but you can say globally if you want. Dick, can you start?
I'm going to let them probably answer that. But just looking at where we're at, I don't think we'll have our first client permit, that we have permits that are in the process of getting processed. I don't think the client will have them in hand for another 2.5 years. So if, at 10 years, I don't think we'll be doing an enormous amount. I do think it'll be starting to be material at the 20-year mark.
Okay, so in 10 years, do you think 1 million tons underground, 10 million tons underground, 100 million tons underground, or more?
Yeah, hundreds.
Hundreds, good, okay.
Yeah.
So screwed, but not that screwed in terms of our emissions ramp.
Yeah, if you're trying to get to the 2050 goal, we're going to be putting CO2 into the ground in 10 years in material numbers, but towards the goal, I'm like Adrian. There's a lot of void space between where we are today and where everybody wants to be.
Spoken like a geologist.
And there's sort of some really interesting math I heard. I can't remember who to attribute this to, but this idea again, where we're sitting today, and we have a 40 gigaton problem to solve over the next 25 years, and half of it, basically we need to be half the way there by 2030 to be on track, which means emissions reductions need to be in the order of 20 gigatons by 2030 or 2035. And in that same period of time, direct air capture is going to go from the goal is from about 0 nominally to about 100 megatons. So the whole point is that even with this whole sequestration thing, it really, and I think to Dick's point, it's something that is critical, but probably in the second half of that time frame, because it's the first half has to be about emissions reduction, and then the second half is an acceleration of removal. And so the 20 gigatons versus 100 megatons, the 100 megatons is inconsequential from a climate point of view, but it's that acceleration from 100 megatons to 10 gigatons, which is doing the bulk of the heavy lifting in the second half of that period. So, but again, even to go from 0 to 100 megatons in this period of time is an immense growth of an industry.
Yeah. All right, Robbie. I was hoping for an optimistic ending note. So far, I'm not sure we're there. Let's see what you come up with.
Well, I'll kind of slide in between those two. 100 million tons. Beautiful. And to Adrian's point, that's an enormous acceleration of this industry, but it does some important things. You've shown proof of concept. Now you've got a track record of storage. Hopefully the tailwinds in this decarbonization space, both commercially and from the regulatory perspective, continue to accelerate. And we're in a position by then to have built out, a couple, if not a series of these storage hubs, and those are the things that will permit that in that second decade, that massive acceleration. In a world ideally where we're really terminaling CO2, into these storage hubs, kind of across the U.S. or across North America. Not dissimilar to what we do with crude oil today, but moving emissions, taking them out of the air and off the point source, and moving to these permanent storage and utilization hubs. It's a tough hill to climb, but I think getting to the next 10 years and the progress and where we're seeing that acceleration even today, I think we're all optimists, right, if we're in the carbon capture space, but I do get excited by where this could be headed.
All right, thanks, Robbie. I like that vision of tolling CO2 all over to hubs and getting to where we need to be by 2050. So thank you all again. This has been a fantastic conversation. I really appreciate your time. I'll let everybody go. I know we're 1 minute over. Apologies, and can't wait to see what you guys all do next. So,
Great.
all right, have a good
Thanks,
one, everyone.
Carly.
Thanks, Charlie. Thanks, everyone.
Yeah, thanks. Bye now.